Okay, so we're going to be looking at, I suppose, one of the main applications, if you like, of integration, and that is for finding area. Okay, and specifically, I suppose it's area, I'm saying under the curve. It's the area from the curve to the axis, usually the x-axis. We're going to look at, I suppose, the y-axis as well, but I suppose for ease of kind of saying it, a lot of the time, you maybe hear area under the curve. But I suppose there is obviously that distinction that depending on where I am, if I can be under, it could be above the curve. It's the area from the curve to the closest to kind of the axis there, depending on what our variable or whatever variable we're integrating with respect to. So looking, I suppose, at these first two ones here, or just kind of the explanation to start off with here. So integration can be used to find the area under a curve, and when finding the area, we use the bounds on the x values. So usually that's going to be what we're looking at, is area under the curve down towards the x-axis. And you can kind of see it from the diagram here. The general idea is that if I have two values, a and b, two x values, and I want to find the area created between the curve and those two x values and the axis, then I do the integral of the function between a and b for variable x. And I suppose it's important there as well that that variable that I'm kind of integrating with respect to is the same variable as I suppose the axis that I want to go to and for the bounds that I have. Okay, I suppose I've put a note here as well, is that integration allows us to find the exact area. So we've looked at the trapezoidal rule before, and that can be applied to functions in the same way it can be applied to, I suppose, those general irregular shapes. Because I suppose in theory, I suppose a function really falls under that same description. So the trapezoidal rule is more of an approximation for area. Integration then will give us a more exact value. So we will have questions that we'll see, like the one as an example here, which is a past exam question, which require us maybe to kind of make that connection between the two, and kind of knowing if I'm asked to find area with one thing and then told to make it more accurate, that integration is the way to go. So looking at the example here, we're given a function f of x. We're asked to use the trapezoid to complete the table first of all, then use trapezoidal rule, and then find the area by integration and calculate percentage error. So that's kind of the general idea that we've been seeing here. If I want to fill out this table, I suppose two ways of doing it. I can go to my table function in my calculator and fill in the values, or I can kind of take my function and just fill in the general values for that. So maybe that's what we'll do here. We're starting with 5, so 5 squared plus 12 times 5 minus 27. That's giving me a value of 8. Okay, and I can do the same thing then, I suppose, for all of the other numbers that I have here. So if I just kind of take those for myself here, so 9, this one's going to end up being 5, and this one's going to end up being 0. So we have a nice kind of curve. It's a quadratic curve, peak at 6, and then back downwards kind of in a symmetrical way then from that. Okay, and obviously I suppose we have our answer below here anyway. Okay, so what we want to continue onwards, I suppose, is looking at how we lean into then the trapezoidal rule element of that and that kind of part of it. So starting with my trapezoidal rule, I just need to remember my formula, and the formula is h over 2 y1 plus yn plus 2 times y2, y3, all the way up to yn minus 1. So the idea with the trapezoidal rule is that I look at intervals, so h is the interval width, and they need to be regular width. So here, that's going to really correspond with these distances between the x values here, which are all just a distance of 1. So h is just going to be 1. The y values then are the f of x values, I suppose. Okay, so we know that connection between y and f of x. We are basically looking at the first and last one, so those are my two zeros, and then doubling every other value. Okay, so from our work on trapezoidal rule, and you can kind of look back at that one, but we're basically just applying the rule. We know that there are certain y values that get doubled because they're included in 2 calculations, and the first and last one are only included in 1. It's important to include them even though they do work out to be 0 here. So filling in my value, it's a half times 0 plus 0 plus 2 times 5 plus 8 plus 9 plus 5 plus 8. Okay, so a half times 2 times, let's add that up, 5 plus 8 plus 9 plus 8 plus 5 is 35. And that's going to give me an answer of 35 units squared. I don't know what units I'm working with, but obviously because it's area, I should still be including that idea of units, and I know it's squared because it is area. Okay, so that's us applying our trapezoidal rule. Now we want to apply integration, so that's going to mean integrating the function that I've been given, which is f of x. Let's just write it down here to remind ourselves. Minus x squared plus 12x minus 27. So we're integrating this function. Because I'm looking to find area, I need to integrate it between two values or two bounds. So I look at the x values. I'm looking for between 3 and 9 here. And I suppose even just to consider for a second exactly what we're looking at, we essentially have a quadratic curve with 3 here, 9 here. My curve has those two values as roots. So I'm actually looking for the entire area between the curve there and the axis between those two root values. So it's kind of a straightforward calculation for us there. So between 3 and 9, we want to integrate this function. So integrating the function gives me minus x cubed over 3 plus 6x squared. So let me see, maybe we'll actually just take that one in a longer step. 12x squared over 2, 27x, to be evaluated at 3 and at 9 here. Okay, so let's just reduce that down a little bit. So minus x cubed over 3 plus 6x squared minus 27x, and again, as we said, to evaluate at 9 and 3. So looking at that, minus 9 cubed over 3 plus 6 times 9 squared minus 27 times 9, and we subtract then the area for 3. Again, that calculation, the same as we've been doing before. Okay, we've seen this in our definite integrals, really, this idea of evaluating my integral. So it's no different there. Let me see the solution that I'm going to get for 9 here. Well, let's work it out. So minus 9 cubed over 3 plus 6 times 9 squared minus 27 times 9. That's going to give me just an answer of 0. Okay. And then the solution for 3, so I can change all of these to 3 here, just for ease of calculation. And that's going to give me minus 36. Okay, so minus 36 gives me a positive 36. Okay, which is what we expect because it is area. Okay, we'd be hoping nearly for that positive value here. And we look a little bit more at what that can mean. So 36 square units with trapezoidal rule, we got 35. The last part was percentage error. So to find percentage error, that is error over the actual value times 100. The error here is just 1. The actual value is 36. So 1 over 36 times 100 gives me 2.777. And was I asked any decimal places? 1 decimal place. So around about 2.8% of an error there. Okay, so small error, but an error nonetheless. Okay, nearly 3% of an error there between the two methods. So either trapezoidal rule or my actual integration here. So let's continue onwards. We'll have a little look at some more example questions here and get into then some of the other aspects of the area under the curve that can come up for us. So looking at this exam question, very, very similar to the one we've just done. It's a trig function. I can see that the values there are given in terms of pi. So to me, that is saying, right, straight away, I need to make sure my calculator's in radians. So that would be the first thing I would do. I'm going to be filling in the values here for this table. So it's all sine. So sine of 0 we know is 0. Okay, I suppose that's one that we really should know without having to fill it in. Pi over 6 is a half. Pi over 3 is root 3 over 2. Pi over 2 is 1. 2 pi over 3 is root 3 over 2. Okay, I suppose from what we know about our trig functions, we should maybe be able to fill out the rest of this anyway. And then sine of pi is going to bring me back to 0 again. Okay, so filling in my values there, we can kind of even see, and the diagram does help us a little bit there in terms of matching up similar values. We're using trapezoidal rule here. Okay, same idea again. The formula, same as above. Okay, but I suppose always good practice really to start by writing down the formula just to make sure that we get all those marks going for it. Okay, making sure we write down as well that we know what's happening. H here is the interval width, so it's the width between the different intervals that I have here. And looking at this function here, I suppose the best place to look is going to be from 0 to whatever the first interval here, because that is the width of the interval is pi over 6 here. We can double check it then as well by trying one of the later values, so maybe pi over 3 minus pi over 6 to get the distance between the two, and it is just pi over 6. So my value for h here, my interval width, pi over 6. So let's fill in all of these values. So it's pi over 6 over 2, 0, plus 0, plus 2 times a half, plus root 3 over 2, plus 1, plus root 3 over 2, plus a half. Okay, so that's pi over 12 times 2 times, let's see, so that's 1, 2, 2 plus root 3. Okay, so that's pi over 12 times 4 plus 2 root 3, and getting our overall answer here. So again, fill that in as normal, pi over 12 times 4 plus 2 root 3, and that's going to give me an answer of 1.94954 units squared. Okay, integration next. So we are integrating the function, which is sine x dx, between 0 and pi. Okay, so sine, when we integrate it, is going to go to minus cosine. Okay, so that's one of our integral rules. So sine is going to go to minus cosine because minus cosine would differentiate to a positive sine value. So I'm now evaluating minus cosine pi minus cosine 0. Okay, so let's work out those values. I forget where my calculator is. Cos pi is minus 1, so that's minus 1 minus, and cos of 0, again, we should know already, is just 1, minus 1. Okay, so that's going to be 2, or yeah, going to be 2. So 1 plus 1, which is 2. Okay, percentage error is error over actual times 100. Here the error, 2 minus 1.954, yeah, 0.04, 0.05, 0.046, yeah, that looks a bit better, all over 2, multiply by 100, and I get 2.3%. 2.3% of an error there. Okay, so straightforward enough, following the same idea, looking at kind of those integrals there, and very, very similar, I suppose, to the example question there, working with the trapezoidal rule and comparing that with our areas via integration properly then. Okay, so we'll look at one more example here. So the diagram shows the graph of a function f of x equals ax squared plus bx plus c. 3 regions on the diagram are marked, k, l, and n. Each of these regions is bounded by the x-axis in the graph of f of x and 2 vertical lines. The area of region k is 358. Use integration to show this expression given to us here. Okay, so the first thing I would want to look at here is just the exact area that they're talking about, which is just this area for k. I'm also going to take note of the fact that that area is the area running from x equals 0 to x equals 2. So if I'm going to integrate, which I suppose I'm leaning towards here because it is area that's mentioned, I know I'm only going to be integrating between 0 and 2. Even though the function does continue beyond that point, I'm just going to go as far as 0 and 2 here. So let's have a look at that. So I'm integrating between 0 and 2, the function f of x, and I am expecting the answer to be 358. So that's me taking from this part here that area should be 358. Okay, so let's focus on the integral first of all. Now the function that I'm integrating has a lot of variables. It has a's, it has b's, it has c's. The answer also has a's, b's, and c's, so I'm not going to allow that to throw me off. I know because it's dx here that the variable that I'm integrating with respect to is x, so I'm only applying those integral rules to x. A, b, and c, as far as I'm concerned, constants. I suppose I was told this at the start, they are just integers, so I'm not going to treat them as anything other than just numbers. Okay, so integrating that is going to give me ax cubed over 3 plus bx squared over 2 plus cx to be integrated at 0, or evaluated at 0 and 2. So evaluating at 2 first of all, plus b2 squared over 2 plus c times 2. Okay, and looking at the function here, I can see the first term has an x. If I put in 0, that will go to 0. The second term will also go to 0. Third term will also go to 0. So all of this is simply going to evaluate to 0. Okay, so I can kind of nearly look at that one before actually having to spend any time really working it out there. So let's continue. 8a over 3 plus 2b plus 2c, and we know the answer is 358. Okay, so we have, I suppose, a setup for an answer. It doesn't look like the exact format that we're looking at for yet, so let's try and make that work. The first thing I notice maybe is that we don't have a fraction in our desired answer here, so let's multiply across by 3 to get rid of that fraction there. 358 by 3 is 1074. Very, very close to my answer here. I'm comparing the coefficients and I can see it should be 433. I have 866. That seems like a factor of 2. So let's divide by 2. 4a, 3b, 3c, and I'm getting 807. And that is indeed my desired answer here. Okay, so a little bit of algebra really just is all that's required at the very end there, just to help me kind of answer the very end of that question there. Okay, so we're getting the general idea, I suppose, area under the curve, using the x values, kind of working within the regions that are kind of identified for us. So we have a few little extra bits to look at. We have to look at area with respect to y, which is maybe a rarer question but follows the same kind of idea. And we also need to look at maybe how the area can be affected by being maybe above and below the curve. But I'm going to split, I think, all of those into little videos, just so maybe we have kind of a few short videos as opposed to one really long video. But yeah, so that's, I suppose, area from the curve to the x-axis, and as I say, we will be looking at maybe to the y-axis, and then curves that go above and below the axis, and how we maybe have to adjust our approach for those curves.